Thank you. Good afternoon. It is a pleasure to be here and explain a little bit about my exciting research that I'm very passionate about, and a little bit of my story of how I got here. Okay. Yeah, I'll just keep going. So just a little bit about me. I have a pretty boring backstory, actually. There we go. I was born and raised in Utah, just about 6 miles south of here in the glorious Canyon Rim neighborhood. And I was born into a really hardworking family of makers and builders, and we really took advantage of all that Utah had to offer. We had a wood-burning stove in our home, and so, I guess we contributed to the inversion back in the 1970s. So we're sorry. But we would go to the Uintas every fall and get wood. And my father, pictured on the left, was an engineer, and you wouldn't know it from how he has tied down this very large load of wood with dental floss. But we got home in one piece, so it's okay. I actually spent a lot of my youth in musical pursuits. I played the piano and the cello, but it came to me pretty early that my mind and personality were really more suited toward the technical disciplines. And so I started taking as many advanced math and science classes as I could. And I really enjoyed math. I liked solving the difficult problems and the satisfaction you got with that. And as soon as I took physics, it really opened my eyes to how the world worked, and it made me view how objects interact with each other differently. And so in high school, I knew I wanted to pursue mechanical engineering. And just by kind of looking at all the different possibilities, I decided on mechanical engineering, which I was a bit dubious about because I'd never designed or built anything. And I didn't know anything about cars, much to my father's dismay. And that's what I thought mechanical engineering was about. But nonetheless, I enrolled here at the University of Utah as a freshman. And all my early design courses I wasn't great in, but by the time I was a junior, I had figured it out. And I won a major design competition, and because of that, I won a place in the lab of Dr. Bob Romer. And he was the chair of the mechanical engineering department at the time. And he ran the Bioheat Transfer Lab. And that was the first exposure I had as an undergraduate to research, and I loved it. And we studied using hypothermia to treat cancer. And so what we were trying to do is raise the temperature of tumors by a few degrees, and by doing so, you can increase the perfusion and oxygenation to the tumor. And clinical trials had shown that when you do that, that when used in conjunction with chemotherapy and radiation therapy, that could be improved. And so I started learning how to design devices that could deposit energy in the body. I learned how to measure the temperature using thermocouples and other devices, and how to mathematically model this. And it really turned me on to research and mechanical engineering. I really found my passion in this lab. And importantly, I was introduced to a technology on the right called focused ultrasound. And it was a way to deliver energy into the body non-invasively. So if you take sound waves and you run them at high enough intensity and focus them down, you can elicit both a thermal or a mechanical effect depending on how you run it. So you could thermally ablate tissue or heat it up to cause hypothermia, or you could cause more transient effects with mechanical effects. And it was very exciting for us. And we started to build more and more complex arrays, and we were using a lot of feedback control, what was great, but I was frustrated with the temperature measurement because we were building these thermocouples, and we had this great non-invasive energy delivery device, but we had to invasively put these thermocouples in to just measure the temperature at a couple points. And we really were hoping one day we could get over that. And so, as often has happened at this university, it was really a collaboration between the College of Engineering and the Health Sciences that solved this problem. And we started collaborating with Dr. Dennis Parker, who's in the audience today. And back in the 1980s, he wrote the first paper demonstrating that you could use magnetic resonance imaging to measure temperature changes. And he wrote this paper, and then he went on to other things. But our lab started collaborating with his lab, and we really coalesced into one group. And it took several years, but we developed a technique to measure 3D temperatures with MRI. So on the left, you can see images coming in about every 3 seconds, where you can see this focused ultrasound is heating up the tissue very locally, and we're able to see that everywhere in space. And you can also on the right see that you can track it in time at a single point. And so this was perfect. We now had a non-invasive energy delivery device, and we had a non-invasive way to monitor the tissue. And so at this point, we decided to apply this technology to breast cancer. The reason we did this was for several reasons. One is there were a lot of very interesting technical problems that we felt that we had the expertise to solve. Second, there were many members of the lab with a real personal connection to breast cancer, and we also had some very enthusiastic clinical collaborators. And breast cancer treatment has really evolved throughout the years, from radical mastectomy, where they removed the entire breast and underlying tissue, to more breast-conserving therapies, such as lumpectomy, to more minimally invasive therapies that are done on a more personalized basis, that are very breast-conserving and can be done under image guidance. And so our technologies, we felt, would just fit into that perfectly. So in 2008, Dr. Parker was awarded an NIH grant, where we and this is when I first started my postdoc in his lab, and he allowed me to take a leadership role. And we developed a magnetic resonance guided focused ultrasound system specifically for treating breast cancer. So as you can see on the left, this was our first prototype that was completed in 2012. And it really combined the MRI physics, ultrasound physics, and bioheat transfer that I had learned through my engineering education to apply to this really important health science problem. The bench tests worked great. We turned our attention to a preclinical study, which I designed in some goat udders that you can see on the right. And we were demonstrating that you can not only measure temperature, as you can see on the top, but you could also assess the outcome. So we could ablate large areas of tissue. So we were so encouraged by these initial results that I decided that, well, this is a great prototype, but it is that you can see a prototype made out of plastic. And we needed to make this a bit more robust to be clinically translatable. So like good engineers, I went back to the drawing board. And you can see the engineering drawings for our next manifestation of this, and we call this the Muse system. So this is a completely comprehensive, image-guided, breast-specific, MR-guided focused ultrasound system that is designed to treat localized breast tumors. And this has really been acknowledged by our peers. Just this last year, I received an R37 Merit Award and an R03 from the National Cancer Institute to continue the study of this. This will fund not only the final regulatory testing we need, but also a phase 1 clinical trial at the Huntsman Cancer Institute that we can evaluate this device with. We've also had some international success and some international collaborators. We sold one of these devices to the Institut Bergonié in Bordeaux, France. And they are currently running a clinical trial. So these are the planning images from the last patient we treated in November. And as you can see, we're able to use MRI to image the breast, to target the tumor. We're able to successfully monitor and assess this treatment, and it's going very well. We've treated 3 patients so far, and we have scheduled an additional 12 to 15 that should be completed by next June, and we're already scheduling patients for next year. So as an engineer, my passion has really been to find innovative solutions to improve the human condition. The process of this conceiving of an idea to apply a technology and the design and construction and translation of this to a first-in-human clinical trial has been immensely satisfying for me. In all the patients we treat, the treatment takes about 60 to 90 minutes. The patients undergo it completely awake. They're not sedated at all. They get up off the table, they get dressed, they come talk to us for a few minutes, and they go home. It is very conservative, it's very non-invasive, and it's very satisfying. So my favorite part of my job are the people I get to work with. And I specifically want to acknowledge Rock Hadley and Rob Merrill and Emily Manalga, who are the other engineers who have really put their engineering genius into the design and construction of this. And I also want to thank Dr. Dennis Parker and Dr. Doug Christensen for their mentorship. That has really enabled my success. Thank you.